So, friends, let us continue the discussion on derivation of stiffness and mass matrix from the first principles for an example problem of an offshore structure. We have considered tension-like platforms. In the last lecture, we discussed about how conceptually TLPs are actually designed and developed. To recollect that, let us say make this statement: TLPs are platforms with excess buoyancy, that is buoyancy exceeds the weight of the platform, and this is compromised by initial pretension in the tethers. We wanted to develop or derive the stiffness matrix for a TLP from the first principles. What we learned from the earlier lectures and earlier module. We are developing the stiffness coefficients, taking that we are trying to find out the force in ith degree by giving unit displacement, in jth degree, keeping all other degrees of freedom restrained. So, we give unit displacement in surge, we give unit displacement in sway, and we developed coefficients along the first two columns of the stiffness matrix. Now, let us derive the stiffness matrix for the heave motion. So, the same figure, we have the platform given with an offset and set down, which is happening in this figure. We already said what is our Kij. So, we should give now unit displacement in the heave direction and try to find forces in all effective degrees of freedom, keeping other degrees of freedom restrained. So, let us say in heave direction, K13 will be 0 because no force is developed in surge direction because of unit displacement in heave direction. Let us say this is again equation number 1. Similarly, K23 is 0 for the same reason, no force is developed in sway direction. Because of unit displacement in heave direction. Call equation 2. Now, I want to find what will be the force in the heave direction because of unit displacement given in the heave direction. So, K33 delta, if you look at the figure. Now, when you give heave displacement, there is a set down happening, and that will now cause the change in tether tension. So, K33 delta will be now AE by L of 4 tethers plus these column members will undergo a variable submergence effect. For example, let us plot this MSL here. So, this is the amount by which an extra submergence happens. So, I should say pi diameter of the column 4 into rho w into g into delta. Okay. So, that gives me the volume and this gives me the force now, and there are 4 such legs. So, we call this equation number 3. Now, K 43, K 53 and K 63 will be 0. So, now I have the third column of the stiffness matrix, because the second subscript indicates unit displacement given along the third degree of freedom, which is heave, and I get forces in almost all degrees of freedom as 1, 2, 3, 4, 5 and 6. So, I have now the third column of the stiffness matrix derived. Now, let us go to roll degree of freedom. So, that is the fourth degree of freedom. This is rotation about x axis. Let us say I have a TLP whose deck consists of 4 column members connected by the pontoon members on the top as well as the bottom. So, this is the plan I am drawing. So, let us say the CG of this. Okay. This is my x axis, this is my y axis in plan, and this dimension I call this as plan breadth and this as plan length, and this is my wave direction. Now, I want to name these column members as 1, 2, 3 and 4. We all know that roll is rotation about x axis. So, I want to rotate it about x axis. Let us view this figure, this object from this direction. And draw it here. So, when you try to draw it here, originally the elevation will be the column members, then the top deck and the bottom pontoon. This will be elevation now. Okay. This is elevation. So, naturally this member will be 2 and this member will be 1, because I am viewing this from this direction. Okay. Now, the CG will be located somewhere here. Okay, this is my CG and this is my water level, which I say as mean sea level. Now, I want to roll this about x axis. So, obviously, the new position of the body will be like this. Let us roll it by this way. So, this becomes my column 2, this becomes my column 1, column 1. Initially, I had some tension in these legs, which I call as T 0 plus delta T 4. 4 stands for the fourth degree of freedom. This is T 0 plus delta T 4. Now, there will be new tension in these legs. These values will be T 0 plus delta T 4 and T 0 plus delta T 4 dash. So, the original buoyancy center was exactly acting here. Now, the buoyancy will be shifted because this column will be more submerged than column 2. Therefore, there is a shift in buoyancy. This is a new buoyancy force center. From that line of action, let this force or this distance be S1 and let E be the eccentricity between these two, that is between the old and the new. Let this be E and let this distance be S2. Now, looking at this figure, one can guess the center to center dimension between 1 and 2 is PL, okay, is PL. Now, we have given unit rotation of theta 4, which is roll. The forces could be which is acting as K 3 4 and the rotation which is K 4 4. Let us try to derive this. So, K 1 4 will be 0 because no force is developed in surge degree due to unit rotation in roll degree. It is called equation number. K 2 4 will also be 0 because no force is developed in sway degree due to unit rotation in roll degree. Due to unit rotation, in roll degree, that is theta 4, pre-tension in the tendons or otherwise called as tethers changes. So, change in pre-tension in each leg is given by, you can look at this figure. I am talking about change in pre-tension in each leg is given by delta T 4, which is actually equal to, you can see here this dimension will be PL by 2, okay, because this is PL. So, I should say PL by 2 cos theta 4, because this angle is theta 4, right. So, cos theta 4 multiplied by AE by L. We assume that the change in pre-tension between the nearer leg and the farther leg, that is delta T 4 and delta T 4 prime, both are same. This is an assumption. Now, look at this figure, this value which is the shift between the new and the old CG, I call this as E 4. So, from this figure I can easily say, if this is my H bar, then I can say, if this is my H bar and this gives me theta 4, then I can say this distance is actually E4. So, with this logic we can now say that K 34 will be equal to, this is equation number 7, K 34 will be now equal to delta T4 plus delta T4 prime. So, twice of that, total is 4 numbers, okay, divided by theta 4. So, from the figure we can easily say sin theta 4 is E4 by h bar, and hence E4 is h bar sin theta 4. Having said this, S1 is actually equal to PL by 2 plus E4. Please see this figure. S1 is actually equal to this distance, okay, plus this. Okay. So, I can say it is PL by 2 plus E4, and S2 is PL by 2 minus E4. On the other hand, in simple terms, S1 plus S2 will be actually PL. Okay, that is what S1 plus S2 will be actually equal to PL. Okay. So, now I want to compute the extra buoyancy force created by this, which will be because of the immersed legs, where DC is the diameter of the column member, rho w g and delta, delta is a set down, okay, and there are 4 such legs. Okay. Now, I want to write K 44, which will be pi DC square by 4 into rho w into g into PL sin theta 4, 4 times of this plus T0 h bar sin theta 4, 4 times of this AE by L PL by 2 cos theta 4, 4 times of this. So, let us say this is my equation 9. So, now I have K 14, K 24, K 34, K 44, K 54 and K 64 will be 0, because no moments in pitch and yaw developed due to unit rotation in roll degree of freedom. Okay. This is equation number 10. So, I have got the entire 4th column now of the stiffness matrix. Similarly, I can do it for pitch degree of freedom, which is the 5th degree of freedom. I can straight away write by looking at the same equation, same figure. To get pitch, I should view this from this direction, okay, for pitch motion. So, I should rotate this about y axis, that is pitch. Okay. So, now I can say K 15 is 0, I think you know the reason. K 25 is 0, I think you know the reason. K 35 is delta T phi plus delta T phi dash by theta phi, twice of this, and K 55 is pi DC square by 4 rho w g P b sin theta 4. You know, this dimension, when you look at this, will be P b, okay, P b sin theta 4 into 4 plus 4 T 0 h bar sin theta phi, same as this, plus A e by L P b by 2 cos theta phi into 4 times, same as this. So, I get k phi phi. Now, k 4 phi and k 6 phi will be 0. I think we know the reason for this. Now, I have the fifth column generated of the stiffness matrix is now derived.